at the differences in how drops dry. Some quick background, there are three known convective mechanisms how the drops dry. The first one is radial flow, and that is what gives like the traditional kind of coffee ring shape. It just gives the ring shape, which is caused by just evaporation of and how the particles move towards the wetting line. The second one is the DLVO force, which causes a more uniform drying pattern. The third one is the meringue circulation, which causes a bump in the center of the drop, which is caused a lot based on the surface tension of both the drop and the air. And through these mechanisms, this phase diagram was developed. The people that developed this were actually using like titanium nanoparticles, which is a little bit different than what we were using. So basically what we were trying to figure out is if using like biological molecules kind of followed this diagram, or if it needed some more just kind of tweaking on how exactly like where the ring structure would be uniform or the bump structure. Y-axis is the velocity of the DLVO force over the velocity of the radial flow, and the x-axis is the velocity of the meringue force versus the velocity of the radial flow. So when the radial flow is mainly like in control, I guess, we're going to get that ring structure, which I kind of talked about previously, and then when the DLVO force is dominating or the uniform deposit, and the meringue force will give you that bump structure. We chose to look at the avid and biotin interaction, and we chose this because it's one of the strongest interactions of the biological world. The bond formation is very strong, and it's not easily disrupted by pH, temperature, any denaturing agents. And also it's used in the laboratory and in industry for both detection and purification techniques. Here are some of the first results that we got. Two images on the left are on the glass side, whereas the two images on the right are on the streptavidin side. And you can clearly see a difference, especially in the two bottom ones, which are where the biotin was added to the solution. The control drops on the two top images, you can see that it spreads less on the streptavidin slide due to the hydrophobic surface. The biotin-containing drop spreads a lot more on the streptavidin slide just because of the biotin's high affinity to the streptavidin, so it wants to really bind to it, so it's going to spread more to get more surface coverage. The more uniform pattern is due to the biotin attracting to the streptavidin. Then we looked at the effects of varying the pH of the solution that we were looking at. The pI is about 5 of the streptavidin, so when the pH is lower than 5, you're going to get a more positive charge on the surface, which would be on the left-hand side, the pH 4.4. In that case, the biotin molecule is going to be positive due to the pKa of 4.66 for the COOH portion of it. When you have the two positives, it's going to kind of repulse each other, so you're going to get more of the ring structure. You have mainly the ring structure, but then because of such high affinity the biotin has to the streptavidin, you're going to get those little deposits in there. Versus the solution with the 6.2 pH value, you're going to have the streptavidin surface is going to be negative because the 6.2 is higher than the streptavidin's pI of 5, which is going to cause the surface to be negative. And you're still going to have a positive biotin molecule because you have a negative surface and the positive, just electrostatically they're going to want to bind together. And also with the biotin and avidin, it's going to bind even more, so that's how you get the more uniform structure where the DLVO force is dominating. And it looks very dense just because of the biotin and avidin interaction. But then, rather than using biotin, we looked at HABA, which is also known to have an attraction to streptavidin, although it's not nearly as high as the attraction that biotin has to it. So here, again, you can see with the pH 4.4, you're going to have the positive streptavidin surface, or a slightly positive streptavidin surface. And you're going to have a negative HABA molecule, which again is due to the pKa value of the HABA. Since it's slightly positive, slightly negative, you're going to have a slight attraction, which is why you see kind of around the ring little deposits on the drop. But still, the drop is mainly controlled by the radial evaporation, so you're going to get that ring structure again. pH at 6.2. You're going to have a more negative surface because the pI of 5 is less than the pH of the solution. So you're going to have a negative surface, and your molecule is still going to be negative, so they're going to repel each other and create that ring structure. And because there's not a very high affinity of the HABA to the streptavidin, you don't really see any deposits like within the ring of the HABA attracting to the streptavidin. Lastly, we looked at a structural analog of the biotin solution, which was vitamin C. We couldn't really come to any sort of direct conclusion. Drying pattern is kind of stuck in all three, because when we take into account the electrostatic interactions between the streptavidin and the vitamin C, in the first one we would actually expect to see a more uniform pattern than we do. You see it starts a kind of a ring structure, but we would definitely expect it to actually look more like the pH of the 6.2. And kind of vice versa, we would expect the pH 6.2 to be more of a ring structure, just solely based on the electrostatic interaction between the surface and the molecule, because vitamin C is not known to have any sort of strong reaction to the streptavidin. There's no real way for us to push the equilibrium towards either a ring or a uniform structure. Visually, you can clearly tell that there's a difference between the biotin drops versus both the HABA and vitamin C, as well as the control on the far left. The patterns created by the biotin solutions on the streptavidin slides are very unique to that specific interaction. And we saw that because the pattern of both the vitamin C and HABA solutions were completely different when compared to the biotin solutions. And also we saw that the pH definitely plays a role in the pattern formation. We actually did 5 or 6 different pH values, and the results were kind of on that same scheme, so it was clear that pH had a definite effect on the pattern formation. Some kind of practical uses that we hope this study produce. We have a pattern recognition software that's already been kind of developed by some collaborators we have at Columbia University. And we also did some protein testing with BSA protein, and it showed pretty well protein sensitivity assessment that could possibly be used with cerebral spinal fluid, with possibly diagnosing some patients in a little less drastic way than is now.